everything seems to be working. 11 a.m. and we can continue. Again, if at some point you have questions, right, or you need clarifications, just say something, right? Again, every time I'm happy to hear your voices, right? Standing here in an empty room talking to myself, it's not very emotionally healthy. All right. Okay. So back to the material. So in the previous class, we derived a Lagrange equation, classical Lagrange equation, right? Typical Lagrange equation from Hamilton's principle. All right. Barely look at the example, but enough to sort of to start your solution. All right. And so today we will have to dive deeper, right? It's sort of like at this point, what comes to my mind, I want to quote that you remember Morpheus from the movie The Matrix, right? So let's take the red pill, stay in the Wonderland, and I'll show you how deep the rabbit hole is, right? All right. Okay. Anyway, so in order to make a transition to the new material, right, to the new sort of new material, we need to again recall the beauties and advantages of having Lagrangian formalism. First, again, you don't have to deal with force. You don't have to deal with vectors. All the quantities are scalar quantities, right? Kinetic energy, potential. Second, the form of the Lagrange equation stays the same no matter which coordinates you use. And the last one, it's easier to deal with constraints. I already mentioned to you where are the constraints, and of course forces of constraints are in the transformation equations when you move from Cartesian coordinates to a new set of linearly independent generalized coordinates. So all the constraints are there, and basically that's where you apply those use kind of constraints, and after that you can forget about them. Basically, in that method, you bypass all forces of constraints. They're somewhere inside, they're hidden, right? You don't care about them, and as a result, of course, you lose information about them, right? So from one point of view, if you're not interested in them, okay, it's great. But from the other side, if you want to know, if you want to have some information about those forces of constraints, then of course that method is not good, right? In that method, that information is lost. So as a result, in order to extract that information, so we need to reshake the whole ground of this formalism which we've been developing. So we will have to go to the core, to the Hamilton's principle, and from that level, we'll have to rearrange something in order to have ability to, as I said, to get information about forces of constraints. For example, you want to know the tension in the core, or you want to know the normal force acting on the system and stuff like that, right? So, and sort of ideology. Okay, the idea I wrote on the top, right? And so now we need to present the method of Lagrange undetermined multipliers, right? And again, as I said, we will have to go all the way back to the Hamiltonian in order to change Lagrange equation. And of course, at the end, we will introduce what is called modified Lagrange equation. And using that equation, we can get information, both pieces of information about life of the system, about trajectory of the system, and also we can get information about forces of constraints. So that's the goal of today's class. And then, of course, at the end, we will look at couple of examples. Okay, so, and also at the end of the previous class, you remember we spent like 10 minutes discussing types of constraints. Right? You remember we introduced holonomic, semi-holonomic, and non-holonomic constraints. So now let's start with the easiest constraints, holonomic. Then next class we will talk about semi-holonomic and non-holonomic constraints. We're not going to touch those for super advanced classes, right? So as a result, let's consider a system with holonomic constraints. Right. So let me write. So let's assume that we have a system. With holonomic constraints. Of course, this is one of the key words in this part, holonomic constraints. Right. Okay, so let's assume that we have m. So first of all, we will need n assume coordinates to describe the system, behavior of the system, and let's assume that we have m constraints, equations of constraints, right? So and now holonomic constraints. You remember, you must be able to express those constraints in a nice algebraic form. So let me write it like this: f alpha, which is the function of q1 all the way to qn. So you see n small. Now it's a number of coordinates that we need to describe the system. And for now, actually, just in general, these are not generalized coordinates. It means that they might be linearly dependent. Most likely, they will be linearly dependent. Okay, why we will see, right? But for now, I'm warning, right? And possible time dependence equals 0. And this alpha spans from 1 all the way to m, and m is less than n. N number of coordinates, m number of constraints. Right? Maybe there is a chord and some surface. Right? So we have two constraints, so we can write down two equations of constraints. Right, and so now the goal is we need to incorporate these constraints somehow in our Hamilton's principle. So let's again recall Hamilton's principle and see how we can add these constraints into the Hamilton's principle in order to get modified Lagrange equation, right? So as I said, let's go back to the Hamilton's principle. And this time we're going to use the second form. You remember when I introduced Hamilton's principle, I presented it in two forms. The first one, the system travels along the path along which the action is stationary. And the second form is if you, in the second variation of action is 0 along the true path. It's basically potato, different form of the same principle. So this time, just so that we can try both of them, we're going to use this form. Variation of action equals 0. Right. And so let's, again, let me write also the action, because now we will have to vary it, and it's better to have in front of your eyes. So integral from time integral of Lagrangian, which can be a function of q dots t. I it spans from 1 to n and small. And dt, so that's our action, and of course I spans from 1 to n. Right. And now let's vary it. Right, so variation of I, right, it looks like soon I will have to change my marker. Right, so integral from t1 to t2, and probably I will, no, first let me open the summation I from 1 to n, right, because I'll have to vary each of these coordinates and then each of these velocities, right, so it will be partial derivative of L with respect to Qi, and then variation of Qi, delta Qi. Then this guy plus partial derivative of L with respect to Qi dot and variation of Qi dot. Of course, variation of time, 0, right? You remember the virtual displacement. During the virtual displacement, time is held constant, so we're not varying time. So now I can close this bracket, and of course, still dt stays over there, right? So yes, I varied it, and now it must be equal to 0 because that's our Hamilton's principle, right? So now let me get rid, pretty much now I'm preparing something from the side of Hamilton's principle, because you remember the goal, we need to combine somehow these constraints with this Hamilton's principle. So now I grabbed Hamilton's principle and do some massaging in order to prepare it for merging, right, with the constraints. And then I will grab this and start doing something with these equations, again, in order to prepare to combine with something from the Hamilton's principle. So what I'm doing right now, some preliminary steps before I merged the results. Right. Okay, so for now, let me just, I want to get rid of this dot, right? So let me integrate by parts only the second integral, this integral. This is nice. I like this. I just want to get delta q in this part. Okay, so all right, maybe I will show it this way. So, okay, so I'm just want to work with this integral. So integral, all right, partial derivative, summation. I will leave it here for now. Partial integration with respect to qi dot. Then you see we have variation of q dot. Q dot, it's a time derivative. So since during the variation, during the virtual displacement, time is held constant, so I can easily interchange this differentiation with respect to time and variation. So let me interchange. I can take d over dt outside, and then I will have delta qi. So I will have d over dt, so it's a dot, that dot. And here I'll have delta qi, right? And of course time, dt. So just basically this integral I rewrote. Okay, and now by parts, of course it will be delta qi in partial derivative of L with respect to qi dot, right? Limits from t1 to t2 and minus the second term. So it will be the same integral from t1 to t2, but now I will have delta qi. Then total time derivative out of this function, d over dt, partial derivative of L with respect to qi dot. Okay, dot merged. Let me separate it. Right. And this dt. Wait, not delta, dt. Right. Okay. What's the value of this first term? We have variation of q at the end points. You remember what we have in the Hamilton's principle, right? Maybe I will draw it underneath. So we had something like this, right? So, and we have initial point and final point, right? That happens at initial t1, and this is point at t2. And of course, you remember all our variations, it doesn't matter which you take, they all go through the endpoints, right? So variation of q's at this point all the time is 0, and at that point is 0, because all those curves end up, okay, start here and then up there. So variation of q at t1 and t2, 0 all the time, right? Okay, so I can dump this. So this is 0, and I will explain. So delta qi at t1 and 2 equals to 0. That's the reason. Okay? And now I like this term. I will just plug it back into here, because now I have delta qi, so I can factor it out, and I will have a nice structure which I wanted to have, right? Maybe I will also emphasize over here. So delta qi at t2 equals to 0, and the same at that endpoint. So now back to this, right? So it will be integral from t1 to t2 summation. Okay, let it be over here for now. Summation from 1 to n. Delta qi, let me factor it out here. Delta qi, right? Then this partial derivative with respect to qi, then minus this construction d over dt, and partial derivative with respect to qi dot. So that's, and it's still an integral in time. So dt equals to 0. So that's what we got from Hamilton's principle. Effectively, look, what we've done, it's basically derivation of the Lagrange equation using this form of Hamilton's principle. If all these q's were linearly independent, generalized coordinates, so at this point, I would say something like this. Since these q's are linearly independent, and of course their variations are linearly independent, then this factor, this bracket must be 0. And that's basically the Lagrange equation, which we derived using the first form of the Hamilton's principle, right? But now, these, maybe I should emphasize that these guys are not linearly independent, right? Not linearly independent. They might be, but in general, we're not demanding that, right? So as a result over here, of course, we cannot say that this bracket must be 0, because these guys, not all of them are linearly independent. Actually, we know how many of them are linearly independent because we know that there are m constraints. So it means that n minus m coordinates are going to be linearly independent. The rest are going to be linearly dependent. But we're not reducing to a new set of generalized coordinates in this method. It's one of the crucial parts in this method. We keep all coordinates. You will understand later why. Right. Okay, so that's what I wanted to get from the Hamilton's principle. Let me just sort of highlight it like this, so that I will need it in a few minutes. And now I need to massage equations of constraints in order to get something which can be combined with this in order to get modified Lagrange equation. So now let's leave this alone. Let's leave behind, and let me check if I mentioned everything before I go. Yeah. Okay, so now let's leave it alone, and now let's play with equations of constraints. You know what? I can probably put a new bullet over here. So that's the first bullet, right, to get this outcome. And now I will put the second bullet. Now I will play with constraints. So again, I want to vary it. Let me vary it. And eventually, I want to get out of these equations of constraints a similar structure so that we can combine both results. Okay, so now vary constraints. So let's okay, actually, equations of constraints. But it's fine. Okay, so it will be delta f alpha. Of course, it's a function of q1, qn, possible time dependence. Okay. Of course, we have to vary each of these coordinates, right? So I will have to introduce summation, and summation over I, because we have n coordinates, so summation still I. Okay, can you see it? Yeah, it's still visible. From 1 to n, and then partial derivative of f alpha with respect to qi and delta qi. Okay, so that's the variation. Again, yeah, there is a time dependence, but you remember that during the virtual displacement variation, right? So time is held constant. Yeah, if you try to vary it, you'll get 0. You're supposed to get 0, right, by definition. All right, okay, so now, yeah, maybe I will emphasize again that alpha spans from 1 to m, m, right? So now we have basically m equations like this for alpha equals 1, then alpha equals 2, alpha equals 3, and so on. So we have m equations of this type, right? And in each equation we have n terms. So now we'll have to, as I said, go deeper into this rabbit's hole. So what I'm going to do, I'm going to multiply each of this equation by a different multiplier, which we are going to call Lagrange multipliers. Okay, let me just write for a couple so that it would be clearer. All right, so I will introduce, for example, lambda 1, first multiplier, and I'm going to multiply that multiplier by this first equation, by delta f1. Basically, it will be lambda 1 and summation over I from 1 to n, partial derivative of f1 with respect to qi delta qi. And then I'm going to do with each of these the rest of the equations. And there are m minus 1 of those, right? And of course, then all the way to lambda m delta fm equals to lambda m and summation over this partial derivative and delta qi. Right. So I introduced basically right now those Lagrange undetermined multipliers. Right now we're not imposing any restrictions on those multipliers. I'm not even saying that they're constant. No, they can be functions of maybe coordinates. We'll look at the example. So that's why they're called not constants but multipliers. Right. Okay, so let me write those. All right, lambda 1 and all the way to lambda m. Yeah, it's Lagrange multipliers. Of course,
Professor?
Yeah.
For the, I think for like a minute, you were cut out from the unstable internet. Do you mind repeating what you were saying?
Okay, yeah, good. So, did you hear this?
I heard the top line, but I think you cut out around there.
Okay, let me, yeah. So basically, now at this point, we have m equations of this type, of these variations. For each m, delta lambda, delta f1, delta f2, delta f3, and so on. Now, just for fun, only for fun, we're doing it all for fun, right? We're going to introduce m multipliers. Multipliers, it doesn't mean that they are constant. They might be constant, but we're not imposing any restrictions on those multipliers. Just, again, they can be constant, they can be functions of coordinates, it can be anything. That's why they're called multipliers without saying anything more, right? So, for example, I will take lambda 1, first multiplier, and multiply it by the first variation of the first equation of constraints, right? So lambda 1 delta f1, and you see it, right? I just, instead of instead of alpha, I use 1, right? Okay, then, of course, I will do exactly the same for the second equation, and I will introduce lambda 2, and then all the way to lambda m. So these multipliers we called Lagrange undetermined multipliers. Right. Okay. All right. So now, what else can we do? All right, to make it look worse, to make it look more complicated. Right. Basically, what I'm trying to get the same structure as what we got from the Hamilton's principle, so we can combine them. So now, what we have? What else? Delta q's are over there. dt. So it means that we need to. We will have to integrate them. Then also, here there is a summation over I over there. It's great, right? So what I'm going to do, I'm going to also hold it, guys, right? If you vary, they must be equal to 0. Okay, now I realize that I forgot to move that 0 over here. Right? I was focusing on explaining what to do. Okay, it must be equal to 0. And now I realize that I forgot to show that 0. Of course, here the same 0, and here must be 0. Right. Okay. Okay, so now, as I said, let's now add all those equations. Or we can first integrate each of these equations with respect to time. If you integrate with respect to time, each of these equations, it will be still 0 on the right-hand side. And then we can add all these equations, right? Or we can first add the equations and then integrate. It doesn't matter, right? So let me write. So let's add them and integrate. And of course, integration over time. Integrate over time. Because again, the idea is to get exactly the same structure like what we got here. Right? So now, and of course, it will be still, right-hand side will be still 0 because all these manipulations are not going to change the value of the right-hand side. It will be still 0. Right? Okay, so now let me start with the integral from t1 to t2. All right, summation over I. Let me also do the same. So summation of I will be outside. You know what? Maybe I will do it step by step because I'm afraid that I might lose something, and I don't want to just rewrite from the notes. Yeah. So let me do it step by step. So summation first over alpha from 1 to m. So that's basically describe the fact that I added all these equations. Again, why not? I'm adding 0, and the right-hand side is 0. Right? Why not? Right. So that's now lambda alpha. Right. So it's this. Then summation over I from 1 to n, partial derivative of f alpha, and with respect to qi and delta qi. Right. And then since we integrated, so I need to add dt. Right. Okay, so that's what we're getting. Let me check. Yeah. And so now, yeah, of course, again, why I keep forgetting this 0? Because trying to focus on explanations and sometimes forget the small details. So now, this is just, yeah, it's complicated, but it's 0. 0 can be added to anything. 5 plus 0 is still 5, right? So, but here we have this construction. So we can add 0 over here easily, right? So I can write plus 0. What a big deal. And of course, inside of that 0, we have all these mass. So let's do it. Let's add that equation, okay, that 0 to this. Or you can say, let's just add this equation to that equation. Oh, you can say any words you want, right? To justify, right? Right. Probably I will, let me put something, some symbol that, some asterisk, for example. Right. So, and now let's add it to that sign, that asterisk. Right. Okay, so as a result, of course, I will have to rewrite it. So it will be integral from t1 to t2. Right. Summation over I want to take outside. So let me start with summation over I from 1 to n, delta qi, and then the rest, except for dt, I will combine in the brackets inside. dt will be all the way at the end. So, and also, let me flip the order of these terms, right? It still equals to 0, right? So I can multiply by -1, and this will be positive, this will be negative. It's not a big deal, right? So let me flip order of these terms. So it will be, as a result, d over dt. It's basically in an attempt to get exactly the same what the book presents. Partial derivative of L with respect to Qi dot, then minus partial derivative of L with respect to Qi. So that's contribution from the Hamilton's principle. And now contribution from this, right? So plus, because I added, right? So plus summation of alpha must be there, right? Summation of alpha, lambda, and this partial derivative. This delta Qi is already here. Right? So summation over alpha from 1 to m, lambda alpha, partial derivative of f alpha with respect to Qi, and yeah, that's it. Right. And dt equals to 0. So, right, the major part we managed to get through. But now there will be plenty of justification and explanations and funky moves. So basically now instead of this form of the result from the Hamilton's principle, now we got this. And now our equations of constraints are inside of this principle. So now, of course, it looks like, of course, we want to say, right, since it's 0, maybe this bracket must be 0. But we have to be careful because you remember what I wrote here. These q's, q1 and all the way to qn, they're not linearly independent. We keep all coordinates. Although we know that there are m constraints, but we still keep all coordinates. So these variations, as a result, they are not linearly independent. Some of them, of course, linearly independent, but n minus m of them, m of them are linearly dependent, right? N minus m linearly independent and m dependent. So as a result, it would be a crime to say, okay, so that factor this bracket must be equal to 0. No. So we have to carefully justify this fact, this step. So first, let me kind of filter these coordinates. Let me first write those which are linearly dependent and then linearly independent, or the other way around. Let me check. First independent. All right. So I will write Q1 all the way to Qn minus m. These are linearly independent. Independent. And then, of course, the rest are going to be linearly dependent. So from Qn minus m plus 1 and all the way to Qn, these guys are linearly dependent. So basically, again, if we had only independent coordinates, this would be easier, right? So we could have just said, okay, this bracket must be 0, right? Because these are linearly independent, right? So these are good guys. But because of these bad guys, basically we cannot make that statement. These guys, troublemakers, they ruin the whole picture, right, for us. So how can we get rid of terms next to variations of these coordinates? Of course, we need to have some killing tools, right, to get rid of these bad guys, of these linearly dependent coordinates, linearly dependent coordinates. And we already prepared those tools, right, those weapons, right, to get rid of these guys, right, where we introduced those. Actually, I didn't write. I started writing, and then you asked to repeat, and I forgot to write Lagrange multipliers. Multipliers, right? So basically, these guys, Lagrange multipliers, can help us to get rid of terms related to these bad guys. Which way? So again, as I said, we have here what n n terms like this, right? And we have these m terms out of those m terms out of n terms are sort of bad one. But at the same time, we have m Lagrange multipliers. We haven't imposed any restrictions on them. We can make them look any way we want, right? So let's choose lambdas in such a way so that factors next to variations of these coordinates are 0. Let's just kill all those terms which creates troubles in these equations. Let's get rid of them by choosing properly Lagrange multipliers. We have freedom with those Lagrange multipliers. Let's use that freedom to get rid of the terms related to these coordinates. So as a result, we can write, basically we manually, artificially making m brackets like this 0 by choosing correct lambdas, right? So now, second step, once we manage to get rid of these bad guys using those those tools, right, those multipliers, now what will be left in this equation? Only terms related to these good guys, linearly independent, right? And of course, if now we have only terms related to linearly independent coordinates, of course, then we can say immediately that factors next to these delta q's must be 0, otherwise it's impossible, right? Because you remember, like, for example, if you have, let's say, in three-dimensional vectors, let's say you have a I hat plus b j hat plus c k hat equals to 0, right? So since a, j, and k are linearly independent, so it can be only correct when a, b, and c equals 0 identically, right? So that's what we'll have at the end, right? Once we manage to get rid of those terms. So you will have only linearly independent terms connected to the linearly independent coordinates. So as a result, those factors, these brackets, must be identically 0. As a result, we have two steps, and as a result, we can make this bracket 0. We can call that this bracket must be equal to 0. And again, lambdas help to get rid of, to make these brackets, m brackets 0, and then the rest will be automatically 0 because the rest of the coordinates are linearly independent. Right? So now justification is a little bit trickier, right? But I think you got the idea, right? So, and that's why we introduced those Lagrange multipliers. Actually, yeah, we introduced them to get rid of these factors. Why? Of course, I will tell later, right? Because they will help us to find forces of constraints. So, as a result, let me. So, what's the time? Okay, we still have plenty. All right. Okay, I'm not going to try to write something because it's. Or maybe I will do. You know what I will do? Yeah. Okay. So we can choose lambdas so that the coefficients of
Professor,
yeah.
it's still cutting in and out like pretty frequently now.
Okay,
Every
I
couple
see.
seconds.
I see the bar at the top of Microsoft Teams internet. That's why I asked at the very beginning. Okay, I'm not using Wi-Fi. Everything is connected with cords, right? I'm not running anything except for that. Okay, now it disappeared. Right? Okay, if it's appears and stays, okay, just remind me, and I will just wait until it gets better, right? Because I cannot control that, right? It's outside of what I can do, right? In my part, everything is connected through the cable cords. Everything is turned off except for what I need for streaming, right? But I cannot control Comcast, right? I can blame them, of course. But at least it gets restored, right? Everything is fine. It's not like at the end of the previous semester in one of my physics 2 recitation classes, pretty much the whole class it was like that. But luckily it was just only one class. Okay, so we can choose those lambdas so that coefficients related to these guys vanish identically. So which way I wrote it, let me just repeat it. Coefficients of a delta q n minus m plus 1 and all the way to delta q n. So coefficients of these variations vanish identically. Basically, we kill these terms, right? Using those lambdas, since we had freedom to choose any lambdas we want. And of course, the rest, the remaining n minus m variations are independent, and the coefficients of each one must vanish. All right, so the remaining, because it's probably the trickiest part in terms of understanding, it's better to write something in a couple of sentences. The remaining n minus m variations oops. No, it's good. Variations delta q1 and all the way to delta qn minus m are independent. So the coefficients of each one must vanish. Of each one must vanish. Right. Okay, so it should be enough, right? So in order to understand, and so now I need to, I guess I don't need all this. I can start erasing. And so now we can write what is called modified Lagrange equation. So what is inside of that bracket, of those brackets? That's what we wanted, modified Lagrange equation. Equations, because of course there are n of them, because we have n terms. Yep, I can erase all that. Still afraid to erase something which I might need. I think I can erase everything. Okay, still good. Right. So, as a result, so I can write d over dt out of partial derivative. It's a qi dot minus partial derivative of L with respect to qi plus, right, summation over alpha. Okay, alpha again runs out of over number of constraints. Then undetermined multiplier, and then partial derivative of f alpha with respect to qi equals to 0. Whew. Right. But troubles are not over yet. let's count how many equations do we have. Basically, I shows which equation, number of equations, right? So I runs from 1 to n. Okay, I erased it. Okay, let me write it here. I runs from 1 to n. So we have n equations. How many unknowns do we have in these n equations? First, all these coordinates, which describes, of course, evolution of the system, life of the system, right? So, and of course, there are n of them. So we have, all right, so n equations, and so we have n q's, but also we introduced our killers, right, of those additional terms. We introduced those undetermined multipliers. We introduced those lambdas, and there are m of them. We also need to find them. Yeah, we said here in words, yeah, we can choose lambdas so that those factors are 0. Yeah, those are words. We will still have to find them eventually. So those are also unknowns. So we have n plus m unknowns. I'm not fitting, right? Unknowns. Right. So qi and lambda m. So the system is not complete, unsolvable. We have more unknowns than equations. What can be done? Okay, mathematicians are smart, right? So they just decided, you know what, we still have those m equations of constraints. Let's just add them to this system. And as a result, we'll have n plus m unknowns and n plus m equations. And it works. So, so we can add f alpha, q's, which are function of q's and t's. So now this is a complete happy system. Okay, this 0 looks ugly. Let me change it to decent, because these are result, and you know what, I can frame it probably. Let me remove this figure bracket, because that's something worth of framing, because that's right. So that's okay. Maybe I should write also over here. So modified Lagrange equations. So these are modified Lagrange equations. Modified Lagrange equations. Right, so that's what we wanted. So let me check if I mention everything, and then we will start looking at example. Yeah, that's what I needed to mention. Again, so what this is, effectively, it's a generalized force. This is generalized force. And these lambdas, yeah, I called them, insulted them, we calling them killers, right? Now, those are just forces of constraints, reaction forces like tension, normal force, friction, right? So we will look at the examples where we can get those forces, right? Of course, some students expect sort of like a formalism, right, which would tell you, okay, so this is the normal force, this is the tension. No. None of the formalism can do it. Even Newtonian formalism doesn't do it, right? So you basically need to know the nature of interactions, and you introduce those forces by yourself into the game, right? So here we will be getting something, but of course, identifying them, of course, you need to see which force is that, right? But anyway, so these lambdas are going to give us basically the magnitude, the value of forces of constraints. So in order to get the directions, right, you'll have to run some additional analysis, right? At least Goldstein doesn't go into that mess. I remember when I was taking the course, I remember our professor explained a little bit, right? So what can be done, but absolute value is also good enough, right? So those are forces of constraints. Let me write that down, something about this. All right, so those lambdas, lambda, okay, we used alphas, right? Lambda alpha. All right, they determine the reaction forces, basically forces of constraints. Yeah. And let me emphasize magnitude. They give us just a magnitude. Okay, maybe magnitudes. Right. Also, uh, some of you might read a different book, right? Different books, right? When I was studying, I remember I had tons of books usually, right? Everything that was available in the library, I would just take it. Okay, some of the books present this modified equation in a slightly different form. Instead of plus, they use minus. So when they move this term to that side, that term is positive. It's not a big deal because what are we basically getting? Magnitude. So plus or minus, who cares, right? This book, all right, Goldstein uses equations in this form. Right? So what else I wanted to mention? Okay, maybe I should also say that this term, basically, this whole thing is a generalized force. Right. But of course, the force itself is inside, right? So what else? Okay, so now examples. So, you know what? Yeah, I'll probably start from on this side. So I will put a big bullet. And like before the class, I was talking, right, to some of you. In this course, derivations can be complicated, right? Can be confusing occasionally, right? Or maybe not confusing. But again, at the end of the day, what is required from you, what we require from you is the ability to solve particular problems. So you just need to use the final result, and that's it, right? And again, it's not like when I was a student, we had to pretty much derive everything, pretty much by heart, right? And then, of course, also showed the ability to solve problems. Right, so as a result, at the end, it's not that bad. But of course, problems are also not completely trivial. Of course, still requires some efforts and time. So the example, yeah, as I said, let me write example. Cylindrical surface. Typical example, right? You solved it using probably Newtonian formalism. In undergraduate level course, I solved this problem using Lagrangian typical, no, Newtonian formalism, sorry, right? So then there's a particle or the puck on top, right? Then you release it and slightly push it, and of course, no friction, right? And then, of course, that puck starts sliding down. And of course, at a certain moment of time, at a certain angle, of course, it flies off from the cylinder, and of course, it will fly, right? So, of course, we need to find the angle at which that departure happens. So, and so now, of course, we will have to use a method of Lagrange. We have to use Lagrange undetermined multipliers because the classical method, in the classical method, you cannot get information about the force, normal force in this case, right? And of course, as a result, you cannot predict where the particle is going to depart, right? So I need to probably draw the picture first. All right. Trying to estimate the amount of space that I might need. So this is my cylinder, ugly. And I will need some space over there, so let me move slightly this side. Okay. Right, so this is the center. Okay, so now I need a coordinate system. Y, X, right? Then radius is A, so this point is A, this point is minus A. Right? Then some position of the point of this spark at some arbitrary moment of time t. Okay, let's say it's at the moment of time t. So it's there. Right. And again, if you use a standard Lagrange equation, standard approach, of course, in this case, it's a effectively one-dimensional problem, all right? Because r is constant, r is fixed. And you use that constraints from the very beginning to write Lagrange equation. And you use only usually this angle as your generalized coordinate, right? It's a one-dimensional system. But in this approach, we're not reducing number of coordinates to a new set of linearly independent. No, we keep them all. It's quite often students misses that point. Students miss that point as a result. Then, with exam, there are problems with exams and so on, right? So we want to keep both of those variables. So we're going to treat r as just a variable, right? Still, we're not going to impose that constraint, the fact that r equals to a immediately. No way. We're going to first write the Lagrangian without using constraints. Okay, in this case only one constraint. R equals a, right? Okay, so let me write. So we have r and theta, which we wrote just two coordinates. And I will emphasize two linearly dependent coordinates. We keep them all. Again, we're going to impose equations of constraints only when we get basically Lagrange equations. Only then we will start applying those constraints. Not from the very beginning. Lagrangian is written in terms of all these coordinates. Okay, so writing the Lagrangian is very simple. Of course, in order to write potential energy, I need to show the reference level. I'm going to position my reference level, of course, at the bottom, right? So potential energy, of course, will be a positive because it's above the reference level. So it will be mgr cosine theta. Lagrangian is, kinetic energy is trivial because basically it's a velocity in polar coordinates. What can be easy? It's back, right? Because I almost started cursing. But it still shows the sign of bad internet quality, bad network quality. Maybe I need to call to Comcast, although it happens like first time in long time. Lagrangian. So L equals T minus V, right? And kinetic energy, it's a one particle, it's m over 2. Again, if it's a one particle and if system is not coupled, there is no point of deriving velocity in polar coordinates because sometimes I see students spend like 5-10 minutes getting that using transformation equations and so on. It's such a mess. No, in this case, you should be able to write immediately. So it's a r dot squared plus r squared theta dot squared, and of course then minus potential energy, right? Minus mgr cosine theta. Right. So the Lagrangian written in terms of linearly dependent coordinates. Right. Okay, let me frame it. And now that must be applied carefully, right? Modified Lagrange equations with equations. You know what? Let me write immediately equations of constraints, and then I will just add to this. And I'm going to write in this form. On the right hand side, we have 0. So in this case, I will write it this way. So f1, because there is only one equation, so it will be a minus r equals to 0. So that's our equation of constraint. Okay, so now modified Lagrange equation. Probably I will start writing immediately in terms of r and theta. So d over dt dl over dr dot minus dl over dr. And then on this side, I keep it on this side. Okay, so plus m equals 1, so this summation over alpha disappears because we have only one equation of constraints. You remember, m counts number of constraints, n number of coordinates, right? So summation, okay, maybe I will write, so summation from alpha from 1 to 1, right? So lambda, no, it's too cheesy right now. Lambda, subscript I will drop because we have only one lambda. Right? Since we have one constraint, of course, we're going to have only one multiplier. And then partial derivative out of that equation with respect to r. You see, downstairs, it's all about r. Here, r dot, r, and r all the time. Right? So equals to 0. So then, of course, let's write similar for the theta dot minus partial derivative of L with respect to theta plus lambda df1 over d theta equals to 0. It looks like, I need to change my marker. It's getting too light. All right, and of course, as I told you now, we need to add, of course, equation of constraints at the bottom. So a minus r, okay, so much bright, contrast is so much stronger. Right. So df over dr, f over dr, it's a minus 1. So this is minus 1, negative 1. And of course, since there is no theta dependence, of course, this is 0. Right. Okay, so now let's write explicitly these equations. I don't need it all. So now every time I'm trying to look over my shoulder at the computer, it's like afraid that that Microsoft Teams or the internet will stab you from the back. So now we have to carefully differentiate. So r dot, it will be mr double dot, right? So this will give us mr double dot, right? Then, correct? Yeah. Then minus dl over dr, minus, and we have r present here and there. So there are two terms. We have to be careful. So it will be mr theta dot squared, mr theta dot squared, and then here again there will be minus mg cosine theta, right? Yeah. And that's lambda. I will probably move to the other side. It will be, of course, minus alpha on this side, but I will move to the other side. Yeah. Now why not? Right, lambda. Now the second. D over dt. Okay, I will keep d over dt. In a second, you'll see why. So, because now we have to differentiate with respect to theta dot. It will be mr squared theta dot, right? Yeah. Why I haven't opened immediately? Because here r is a function of time and theta is a function of time. So we have to, of course, if you want to open it up, you have to be careful. Right? And I don't want to make silly mistakes. So then, with respect to theta, theta is only here. So we have minus in front. Then minus from here. And then when we differentiate cosine, we will get another minus. So we'll get minus. So it will be minus mg r sine theta equals to 0. And of course now, after getting these equations, only now we can start applying our constraints. So now r equals to a. Then of course if you differentiate, you will get first time r dot equals to 0 and r double dot equals to 0 as well. Right. So again, in the standard Lagrangian approach, you apply these constraints immediately when you write Lagrangian formally. Lagrangian here only once you wrote down Lagrange equations explicitly. So this will be 0. Okay, let me. So this is 0. Then minus m a theta dot squared. Then plus mg cosine theta plus mg cosine theta equals to lambda. Okay, let me check if I'm getting what I'm supposed to get. Yeah. So now the second. Of course, you can open it by differentiating with respect to time, but actually if I plug it, it will be the same. So I will get ma squared theta double dot. Right. So it will be ma squared theta double dot, then minus mga sine theta equals to 0. So now we applied it. Right. Again, let me check the second equation. Yep. Okay, so that's equation number 1. Now equation number 2. 2 unknowns, 2 equations, so we're all set. Right. So we have theta and lambdas are unknowns. And again, what we want to get, of course, we need to get lambda, which is normal force. Why is it normal force? Because it is present in the equation for r. So it's related to this direction, which is the normal force, right? So we need to get lambda as a function of theta, and then of course you need to look at the point where lambda disappears, where lambda becomes 0, right? So now how can we combine them? And again, I need to get rid of theta dot. So what I'm going to do, I'm going to differentiate the first equation with respect to t, so that I can get also over there a theta double dot and remove it. Right. So d over dt out of that. So out of the first equation. And so as a result, we will get, right, okay, so it's this, and now this will be minus ma 2 theta dot, right? And then theta double dot. Right. So it's this term. Now that term, it will be minus mg sine theta dot. And, okay, you remember I told you when we introduce lambda, we're not telling that that is a constant, or it can be a function of all these variables, r and theta, right? So let me emphasize that that can be a function of lambda, can be a function of r and theta, just a multiplier. So let's differentiate that properly. Of course, over here, I'll have to write, so d lambda over dt, right? Oh, d lambda, just a second. D lambda over, why I keep writing partial? All right, over d, theta dot plus d lambda over d r dot. And of course, r dot is 0. So the second term is, right, it's 0. And also, what's left, we have theta dot, theta dot, theta dot. We can remove them. Right. And as a result, we will have, okay, let me rewrite, and again, together with this second equation, because now it's kind of messy. So it will be minus 2ma theta double dot minus mg sine theta equals to d lambda over d theta. And underneath, let me write this equation. So it will be ma squared theta double dot minus mga sine theta equals to 0. So now that's what we have. Okay, so now in order to get rid of theta double dot, okay, let me just hold you for a couple of minutes. So the second equation must be multiplied by what in order to get exactly the same term? 2 divided by a, right? Yeah, 2 divided by a, and as a result, we will get exactly the same first term in both equations. So if you add, and then of course you will add these two equations. Okay, so the first term disappears. The second one, negative 1, here negative 2, so it will be minus 3 mg sine theta and equals to d lambda over d theta. We can integrate this easily with respect to theta, right? Okay, so now, of course, you can get that lambda as a function of theta now only. Right. So it will be, okay, I will just grab my notes. So it will be equals to 3 mg cosine theta and plus some constant of integration. Okay, how can we find constant of integration? Again, we need to apply our sort of conceptual analysis and sort of realize that when the block, okay, this puck is at the top where the surface is flat, of course, the normal force will be equal just to mg. You need to know that in order to get that constant, because what? It's a constant of integration, and this is the reaction of the surface. It's a normal force. You need to know something about that normal force. Otherwise, you wouldn't be able to get that constant, right? So at the top, where theta equals to 0, lambda at theta equals to 0 equals to mg, right? So we need to apply that, otherwise we wouldn't be able to solve it, right? So mg, so, okay, yeah, we'll just continue. So basically I'm applying immediately to this equation. Instead of theta, theta equals 0. So that's the answer. This term is going to give me cosine 0, 1, so it will be 3 mg plus c. So from here we can get c as minus 2 mg. So that's the constant. And so now we can write explicit function for lambda. So it will be 3 mg cosine theta minus 2 mg. So that's the how normal force changes with angle, right? So that's the normal force. Again, identifying that it is normal force, of course, it's a you have to do it. And of course, the angle at which point flies off from the surface, we can easily find by putting lambda to 0, because lambda must be a non-negative. Right. So it flies off when lambda equals to 0. Right. or maybe you know what, lambda as theta critical, some kind of theta sub c equals to 0. Right? Okay, so last half a minute. So it will be 3 mg cosine theta critical minus 2 mg equals to 0. Of course, from here we can get easily the angle 2/3. So cosine of theta critical equals 2/3. So arc sine of that gives us the angle, critical angle at which this puck is going to fly. So that's the first example where the equation of constraint depended on only one variable. So next example, we will look at Atwood Machine. In that example, there will be again one equation of constraints, but it will depend on two variables. Right. So of course, as a result, in that case, Lagrange multipliers are going to appear in both of equations, not just in one, like in this case, right? So since normal force, right, is connected to the radial direction, so it appeared only in the radial equation and nothing in. But if we, for example, had some friction over here, right? For example, maybe there's a wheel rolling down. In that case, the friction force acts in the tangential direction. Of course, it will appear in the equation for theta.